let's just get straight into this one. So this is number 21 on practice exam 3. So what happens here is we get a pendulum and it's raised to height L from here. So it's a simple pendulum, and so we know it's affected by gravity. And it's asking us for when kinetic energy is equal to potential energy. Well, we know here that the mechanical energy is going to be equal to m times g times L, because L is the height. So when kinetic energy is equal to potential energy, it's going to be me is equal to kinetic energy times 0.5 plus potential energy times 0.5. So we know that the potential energy times 0.5, that's going to be here at 0.5 L. So now it asks us to find the angle which just happens about when we get here. So let's divide this into around 45 degrees. Even though that's a terrible job, we're going to say that's 45 degrees. What we're going to do is we're going to take the sine of this ratio. So sine of 45 degrees. If we put that into our calculator, it's going to give us 0.7 or root 2 over 2. So it can't be 7. And since it's greater than, I'm going to go to sine of 30. This, you just have to know what your unit circle is. Sine is just going to be the y values. Sine of 30, if we put this in a calculator, it gives us 0.5. So we know that theta has to be less than 45 degrees for the potential energy and the kinetic energy to be equal. So this angle has to equal 30 for it to be at 45, to be 0.5 L. 45 degrees is actually going to be like around right here. So our answer is going to be C, less than 45 degrees. Question number 22 is going to deal with a force times momentum graph. So it gives us a graph that looks something like this. This is negative 8, this is 4, this is 14, this is 20. And so it gives us this, and then it goes straight here, straight to negative 8, up, dot, dot, dot. So for us to understand this is force, this is time, we need to understand what force really is. So force, the way Newton originally wrote it, was the derivative of p in respect to time, which if you just rewrite it, that's just m times d dt times v, which will give us m times a. So that's why we are able to compute the integral of this to get the answer. So let's just take the area under the curve right here and the area under the curve right here. Well, we can see that the momentum is increasing here and decreasing here, so that takes off A and B right away. Now we just need to find if it reverses or not. So what we're going to do is we're just going to do 4 times 14 plus 6 times negative 8. 4 times 14, that gives us 56, plus 6 times negative 8 will give us negative 48, which when we add those together gives us 8. Therefore, it does not reverse direction because this is still positive and it's positive at the beginning. Moving on to question number 23. So question number 23 gives us a velocity times time graph. And it asks us to find when the thing in motion gets back to its original position. 1, 2, and this is negative 1, this is negative 2, this is negative 3. Here we're just going to estimate at the beginning. So we can see here that it starts at around 1. So we're just going to label this as 1, and then it pretty much goes to 3 and then stagnates here. And then it goes all the way down to 10 at negative 2, and it stagnates again. So we take the area under this curve to get what position is, because the velocity times dt is going to give us x. So when we do this, 1 times 3 times 1/2. This is equal to 3/2. So we need the area under the next curve to be at least 3/2. It has to be this. It has to be 3/2 in the interval. So let's take 5 to 7, because we know it's not going to get there from 3 to 5 first. 5 to 7, let's just mark 7 like about right here. Around halfway through. At 7, it's going to still be at -1. I drew this graph really bad, but on the actual graph here, it's about right here. So if we do, our change is going to be -1, change in time is 2, 1/2. Well, this is equal to -1, so that takes out to 5 less than t less than 7. Can't be that. And if we just look at 10 to 12, the area under this is much larger than that, so the answer has to be 7 less than or equal to t less than or equal to 10. So our answer is going to be C. Moving on to question number 24 now. Question number 24 gives us this fun little triangle force times displacement graph. Goes up here to here, peaks at 16, goes up to here. So the first thing we want to do is we want to get work, because we're going to be using the work energy theorem to find the kinetic energy. So work is equal to our force times our displacement. It's just going to be a scalar quantities, or as it's going to show up on the AP test, fx cosine of theta. And it's also going to be the area under the curve of a force times displacement. Force in respect to the displacement. So what the first thing we want to do is just take the area under the curve, 16, 2. Well, triangle 16, it's going to be base times is 1/2. 2, we can just factor 2 times 1/2. We're going to get 16 for our work. So we get 16 is equal to 1/2. It gives us the mass in the problem 2 times v squared. These cancel out. V squared is equal to 16. V is equal to 4. So our answer is B. Moving on to question number 25. So question number 25 asks us for the acceleration of gravity on a different planet. So what we're going to do here is we're going to use one of our kinematic equations after we look at this graph here. It's just a little dot, 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 dot. All that's important is that this is 0.5, this right here is 3, this is 5, this is the height, this is the time. So what we're going to do is we're going to use a kinematic equation. Y is equal to y0 plus vy 0 of t plus 1/2 AT. So we know there's no original velocity given the equation, so we can just say that's 0. And we know this is 3. So 3 is equal to 5 plus 1/2 t squared times whatever the acceleration on this planet is. So what we're going to do now is we're going to move -2 times, then we're going to multiply this by 2, because that's 1/2, and divide by t squared. It's going to be equal to our acceleration, -4. T is 0.5, so 0.5 squared is going to give us 0.25. Negative 4 times 0.25 is equal to our acceleration. Our acceleration is going to be equal to 16 overall after we take the absolute value. So our answer is B. Moving on to question number 26. Question number 26 asks us the linear and angular velocity of a Ferris wheel rider. And so it's asking us how the linear velocity changes and how the angular velocity changes while it passes through point A. So our linear speed, this is going to be our centripetal acceleration. Bah, bah. So the linear speed, as it's going around this, it's going to change in quantity since it's tangential. So the vector quantity is always going to be changing. So we know our linear velocity will be changing around the circle, always. Our angular velocity, however, will stay constant no matter what. So our answer, if we just look at the chart, it's going to give us D. God dang it. Moving on to question number 27. 27 is also another Ferris wheel problem. For 27, it asks us how, if normal force is greater at the top or the bottom, and if so, what is the normal force exerted on the rider? So what first we have to do is we have to find our force in the y at the top. The force in the y at the top, well, it's centripetal acceleration, it's centripetal, so we have v squared over r is equal to f of g if we say that the positive direction is down, f of g minus f of n. So we get mv squared over r plus f of n is equal to f of g, or if we want it in terms of f of n, which we're going to want, f of n mv squared r negative plus force of gravity. You have to expand out a little. So this is when it's at the top. Now when it's at the bottom, we're going to label that the positive direction is going to be up now, because we can do that. So now what we're going to do is we're going to find how it works now. So if gravity is now negative, our f of y is going to be equal to mv squared over r f of n minus f of g. So then we just get mv squared r plus f of g is equal to force normal. So now we know our force normal at the bottom is greater than our force normal at the top. And now we just need to find how much bigger it is. Well, 1 minus 0.2 is equal to 0.8. This is 0.8 right here. So we can just assume that the same thing, 1 plus 0.2 is equal to 1.2. 1.2 newtons is our answer. Since this is an MCQ, that's all you have to show. You actually don't have to show anything. This is an FRQ, you have to show a more detailed process. Now moving on to number 28. 28 asks us to find the kinetic energy of a rock dropped from the Ferris wheel. So the rock we dropped at position A at the top, and we want to find it at position D. So at position D, it's going to have both kinetic and potential energy, so we can't just rule out one part. So the first thing we have to do for this one is we have to find the mechanical energy at A. So mechanical energy at A, we only have mgh. So instead of using h, I'm going to use r since it's the radius. mgr. The kinetic energy when it hits the ground is going to be equal to mgr. Which is also equal to 1/2 mv squared. Cancel these out. G 1/2. So we want to find the velocity. Velocity is going to be equal to gr square root. So when we find it at D, we know it's going to have both mechanical, it's going to have both potential and kinetic energy. So the kinetic equation that we can be used in this case is V y squared is equal to V0y squared plus two-way displacement. This can be applied to the rock's vertical motion, and we'll just take downward as the positive direction in this case. So there's no starting velocity. Vy squared is equal to 2g times 2r. This is just finding the same thing. Which then we get Vy squared is equal to 4gr. Vy is equal to 2gr. It's the same thing. We can cross this out though, because it's not really useful. Alright. Since Vx is going to be equal to r Vy, the kinetic energy of the rock when it's the same height at point D is going to be to 1/2 m times Vx squared plus Vy squared. So Vy. So this is just 1/2 m V squared plus 4m gr. So that's our final equation. And so our answer is D. Because we don't need that. The answer is D. I'm trying to erase this, it's not really working. Oh, froze. Okay. I'll have to complete this later. That's great. Again, stylus just doesn't work anymore. So 29. We have an equation about the normal force between boxes. So we have the force acting on box here, and the box here. Height of the boxes doesn't really matter. A, B, C. There's a little weight on here, but this weight gets transferred here. So what we're going to be concerned about here is the horizontal forces exerted on block A and block B and block C. The horizontal forces exerted on block A when we switch it to C is going to it's going to be the same, because the horizontal forces is going to be normal. This here, it's going to stay the same. This stays the same. However, when we add it to C, BC, the force acting on BC, the normal force acting on here, will now change. So this will increase. Doesn't really make sense, but it's how it works. And finally, last question of this video is going to be question number 30. Question number 30 is distance traveled by an object. Gives us this, here, here. Then it gives us acceleration 2, and 2 here, 1 here, a bunch of dots lining up to here, and it goes down, and then lands here. So it asks us for displacement. So what we're going to have to do here is there's two ways to do this. We can do this the geometric way, or we can do it the calculus way. I'll show both how to do both ways coming up here. So the way we want to do it, the geometric way, is what we're just going to do is we're just going to go here. We see the slope. This is going to be our velocity graph. Slope here is 2, so we're going to take slope to 1, and then we're going to go like this. And this is 1, this is 2. The area under the curve here, area under the curve is going to be 1. So that's why it goes up to 1, and then it goes here. The area under this curve is going to be equal to 3. If we do it this way, which is the technically physics way to do it. There's one way to do it. That's how you're going to get this answer. And the curve here is actually, this is actually 2, I lied. However, if we want to prove this, why this works, we do this the calculus way. And so we're going to write our equation for what acceleration is. So acceleration here, acceleration to t is equal to 2, 0, less than or equal to t, less than 1, and 0, 0, less than 1, less than or equal to t, less than or equal to 2. So what we're going to have to compute here is what we call double integral, and we're going to do it in 2 ways. So first one we're going to do is a double integral 0, 1, 0, 1, 2, dt plus 1, 2, 1, 2, c dt. So once we take this first one, we get integral 0 to 1, 2t from 0 to 1 dt plus integral from 1 to 2 of c from 0 to 1 dt. So now we're just going to do the same thing. We're going to get 0 to 1, 2 dt plus, now we're going to get 1, 2, 1 dt. And if we take those, we're going to get 2 plus 1, which gives our answer 3, which our displacement in respect to time is 3 over this given interval.